Then we can, now from here onwards, we'll start some tips. Tip number one, keep the decoupling capacitor close to the circuit. What I mean here, at the input, we can have a capacitor, which is generally called a decoupling capacitor. So suppose we have a battery which is kept 10 feet away from the circuit. This wire will be very large if it is 10 feet or 5 feet away from the box or from the buck converter. But if within the buck converter, at the receiving end, if we connect a capacitor, so this will avoid the parasitic of all this, because if switch will turn off, all these energy will transfer to the capacitor. That will not really appear across the switch. But still, the decoupling capacitor and switch and this control loop will have some wires, so we cannot avoid, because we need to have some wires or some traces to connect to make a circuit. We cannot avoid everything, but we can reduce it. So we can keep this decoupling capacitor as close as possible to the circuit. That probably from here we can see this decoupling capacitor was kept somewhere. So but this is a DC input. We have a solar panel connected on the rooftop. We have like 5-floor building. Now we are residing in the ground floor. So those wires will come from our rooftop to ground floor. They may be traveling like 20-30 meters of distance. So these traces will be very long. All of that inductance will be there. So we can keep within the inverter circuit, we can keep a decoupling capacitor, which is usually present in all the circuits. Usually you will find a decoupling capacitor, input capacitor, sometimes we call decoupling capacitor. That capacitor should be close to the devices within the inverter we are using. So if we bring them close to each other, we can reduce these lengths, right? This is the important part, switching loop. This length of wire within this should be reduced. Second tip here, a film capacitor can also be used even after decoupling capacitor. What I mean by this, so I'll tell you, but these capacitor film, these additional film capacitor, they can be like class of capacitor should be an EMI separation cap. Generally we call them X2 type capacitor. So what happens here, we have this decoupling cap. So decoupling capacitors are sometimes bulky. They are bigger in size because we need to have larger energy. Like if we take an example of inverter, we need to have a capacitor which should absorb 100 hertz ripple. So this is much bigger in size. While we can use some nanofarad value or 1 or 2 microfarad value of additional film capacitors here, this cannot be kept very near because it itself is a big. It needs a correct placement place and it needs proper routing. But this small capacitor, additional film capacitor, that these can be placed just on the device. Usually you will find in power electronics there are some capacitors connected on the pin itself. Those are additional clamping capacitor, generally we call them. These are film capacitor. Additional capacitors can be used. So the length which was like this long earlier, we have used these two extra capacitors with each of the lag, and you can see this critical trace of this length that is reduced. Now this is remaining red part. So that effect of this we have reduced by using these film capacitors, or sometimes we call clamping capacitors. The value of them is very small. They are smaller in size, so we can connect them very close to the devices, or many times just on the device pin. Second tip. Third, uh, here power devices of a leg must be close to each other, as well as they can be connected to a heatsink properly. So if we can see the distance between these two devices, this is also a critical trace. How
Hello.
we can? Yes.
Sir, you told that after that decoupling capacitor, you are putting in film capacitor, but the film capacitor ESR is quite high, right? So can't we put ceramic capacitor there?
Uh, that depends on the availability. Ceramic capacitor we can use. There is no such issue because both are high frequency separation capacitors. But when we talk about power electronics and when we like go for um such applications, so usually film capacitors are used.
Okay, okay.
So there is nothing like we cannot use ceramic. We can use that. In fact, in some of the places in low power application, I saw it. But for a bit high voltage and high power application, usually I saw mostly film capacitors are used. There should be AC capacitor first of all. So
Mhm. Okay,
that
sir. Okay.
film capacitor. Okay,
Thanks.
thank you. So here we can see this is also critical trace. If we keep these two devices close to each other, we can reduce this critical trace, right? So here also this length we can see in the buck converter, we can reduce this by placing them close to each other. By placing them, so sometimes we have half bridge module. People go for half bridge module. So two devices are manufactured within a single die. We get the benefit of such thing there. Fourth tip, we can use snubbers. Okay, so here also it is many times heard in the industry and everywhere. What happens? My even after putting so many snubbers or everything, system is still not working. Still voltage spike across the switches. They are very high. So what is the point here? Snubber may be helpful, but connection of snubber plays a major role. So one thing somebody can say, okay, I will connect this resistor here and this capacitor here. This is also same point. Somebody can say, I will connect it here. Somebody may connect it here where it is currently, right? Somebody can connect it here. But the right placement or the best placement is that you try to connect it on the pin as close as possible because their values are important, but placement of a snubber is more important than their values. So they should be connected just on. So what I mean here, like suppose we have, I'll just take it separately. We have a switch here. Okay. Now we have to place this RC snubber. I can connect it here. I can connect it here. I can connect it here. So whichever is the closest point of the switch, there we should connect it because then this critical trace, this length, we will be able to reduce it. So the inductance of this path will be diverted through the snubber nicely. If we leave it here, then what about this inductance? This will anyway harm the switch. So placement of capacitor is important. This was the tip number 4. Tip number 5, while designing a PCB, switching circuit and corresponding paths should be away. Uh, Away, I mean, they need not to be physically away because there are other things like we can place them uh, opposite side of the PCB layer. So one type of circuit is on an opposite direction, bottom layer, other type of circuit is on the top layer. So they are not really away from each other, but they are very much separate. And there must be some sort of separation. We can provide a plane within the internal layer, or in fact, we can provide some sort of separation within the two types of circuit. So switching circuit, those are the critical circuit. They should be away, and their paths, switching loop paths should be away or separate from sensing and control circuit. Layout should look like that. high voltage area, high current area, and low voltage and low current area, sensing part, control part, bias supply part have separate rooms. So this is a really physical micro inverter. Here, if we see, you will find this complete room is, if we see complete circuit, we won't be able to identify what is there. But actually, it is presented like this. This part is having only one type of circuit: interleaved, active, clamp, flyback converter. This part is having only full bridge part. So any component of full bridge will not come out of there that room, and it will not go inside this room. All these DSP, I mean controller, will have a separate room. Any component of controller will not go in this room, and any component of other circuit will not come in this room. So such rooms are allotted. They can be, in fact, in the software there are a mechanism we can allot a room. Then if we place any component outside the room, it will give an error. It is our own definition. We can define this is the room for this circuit, and if layout designer, PCB designer is mistakenly putting a component outside that room, it will give an error. Such rooms are provided. Tip number 6, this is about a driver circuit. Length between driver pins and MOSFET or IGBT gate terminal should be as less as possible. This is very problematic. Very problem. Every power electronic engineer who worked on hardware, you will find he has seen this issue. He has experienced this issue. So what happens here? If this length is large, see, we know we have a driver circuit, we have a switch. This driver circuit should operate this switch. We need to use a register, right? Gate register between driver and switch. Okay, what all is there? Nothing. But if we have long trace, then we know there will be an inductor, right? And we also know gate source. There is a capacitor, gate to source capacitor of the device. There may be some additional capacitor between these two traces. We have inductor. Now this, earlier we could see only resistor, but now we can see a very nice RLC circuit, right? So when we give a pulse to this MOSFET, this pulse will not be like this. This will become something like this. Ringing effect will come while turning on as well as while turning off. What you just observed in those DSO pics, some sort of that. And this ringing could be so high, it is turning on and going down to 0. So what will happen? Switch will turn on and turn off again. Then it will again turn on and again turn off. So this 2-3 times false turn on can happen. And this is, since this duration is very small, it really creates large EMI EMC issues. Switch is just quickly turning on and off, and it can sometimes even we won't be able to identify this problem before that switch will blow off. So we should keep this length between driver and MOSFET very small as possible. It reduces line inductance, reduces scope of noise capture.
Sir, I have
Uh,
one question.
yeah.
Sir, even though we have reduced, we have optimized the trace length, suppose if we are getting the same ringing issue, then what we can do to reduce that?
See, we cannot bring it to 0. First of all, we cannot bring it to 0. We can bring it down to really some extent. Like suppose uh, we want this. I just We want this type of smooth pulse, but there may be some effect up to like 1% more or 1% less than that. So there are several measures we can take. We can keep the distance as small as possible. We can also use flat conductor instead of a circular conductor, because if you will see those trace inductance formula, you will find if conductor has flat nature, its inductance is less compared to circular inductor. So we can have these things. We can also have like these two traces can be routed together, like parallel to each other. So they will form some sort of capacitor between them. So those capacitors will effectively reduce the effect of these inductances before going up to switch terminal, before appearing switch gate and source. These inductance will have the effect of inductance will reduce to some extent by these capacitor. Which capacitor? If these two traces are close to each other, again they will be having two conductors. There is air in between them. This will become a capacitor. So these such measures we can take 3 4 measures, but we cannot like bring them to zero, because superconductivity or like zero inductance in the trace, can we achieve that? If we can't achieve that, then we cannot avoid it to zero. It may be small, which is acceptable, which is not really creating any problem, but we cannot avoid it. We can reduce it, and yes, we should reduce it. Okay. Sometimes high current path should be provided by a plane, more thickness instead of a wire or trace. So we can keep something like this. These are two crude PCB I am showing here. We can have plane also, like properly manufactured plane on the PCB or within the layers. Such planes, flat traces are having less inductance compared to circular wires. And tip number 8, positive or high voltage traces should be at a reasonable distance from the negative low voltage traces. So like if you see this IGBT or whatever it is, MOSFET, you will find it has 3 pins. Second and third pin is usually drain and source or collector or emitter. The distance between them is 5 mm. So this much distance we should follow throughout the circuit design. At least. So thumb rule is like 5 mm for 1200 volt. We should follow this much distance. It further depends on atmosphere and the dielectric provided between them. So like here we can see it is just air. In PCB, one terminal is routed on top, another is on bottom. So then we can reduce the distance, and like dielectric and solder mask is provided on the PCB. So atmospheric effect is also reduced. This is like 5 mm for 12 volts. So such thing like point is that positive or high voltage trace or negative low voltage trace should have a reasonable distance. Number 9, low voltage components like driver, sensing, control. All these components are low voltage with respect to power circuit. Should be ground side instead of high voltage side. What I mean, if we talk about high voltage, then we will have zero potential and some higher potential. It may be like 400 volts. So it would be 0 volt and 400 volt. We should keep these low voltage components. Uh, okay, we should keep these devices and component low voltage side, the terminal or the area which is having lower potential. That side we can keep these components. Low voltage terminal can be a plane as well. So we can keep like whatever is at zero potential, we can keep a bigger plane there. Then all these components like sensing, driver, these can be placed that side. So this PCB, what you see on the screen, upper part is high voltage part, like 400 volt. There is some noise. If someone can please mute yourself. Yeah, yeah. Thank you. Thanks. So here in the PCB, what we see, this higher side, upper side is high voltage part, and these are the devices. Below this, all this is low voltage part. So all the driver and sensing and some power supply, small components, you will find that these are placed at low voltage side. Another tip, filter should be connected near the input of receiver, not at the sending end, midway. Uh, can I request someone is some noise I can hear? Yeah. Okay. Uh, thank you. Okay. So filter should be connected. This is also a very important point. Just summary of like maybe several other suggestions like simple summary. Filter should be connected near the input of receiver, not at the sending end or midway. What I mean, suppose we have a sensor. That sensor is supplying some signal to microcontroller. Of course, we will sense and then it will give signal to microcontroller. We usually keep some sort of filters between them. So that filter should be here. Sending end? No. Should that be at the midway somewhere? No. Those filters should be provided at the receiver's side. It should be provided here. Now again this microcontroller is sending some signal to driver. Again filter should be provided at the receiver's end because all the noise captured in these lines uh, here, atmospheric noise or noise from other circuit, all of them will be captured. That can be filtered out just before going into the next device. Like if one example, you might have seen ferrite beads on your mouse or keyboard or maybe sometime charger. So those ferrite bead you will find they are mostly connected at the receiver side because all that atmospheric noise should be filtered out before receiving the signal. Okay. So in short, all supporting components should be as closer as possible to the device or component which is being supported. So, in sensor, we will not only have a sensor. That sensor may have some supporting components requirement. Couple of capacitors need to be connected, couple of registers need to be connected. Microcontroller is not always comes like alone. You will find in the data sheet they will suggest 10 capacitors around it, maybe sometime a ferrite bead or sometime inductor. So those are the supporting components of microcontroller. All those supporting component of microcontroller should be placed near to microcontroller. Should not happen that is going driver side or it is going to sensor side or somewhere else. Like decoupling capacitor is must for all the ICs. Usually find this is the IC, a microcontroller. You will find all the supporting components are close to this, and these are the decoupling capacitors. You can find some of them. Length between decoupling capacitor and respective IC component should be as small as possible. So usually sometime in the data sheet you will find they will suggest 6 mm. Distance between IC and its own decoupling capacitor, distance should be 6 mm or less. Traces between decoupling capacitor and respective IC or component should be as wide as possible. This reduces the inductance and fulfills the purpose of decoupling cap in better manner. So you will see in the figure, you can observe this capacitor is connected to IC with a wider trace compared to other traces. This is also capacitor connected to IC using a wider trace compared to other traces. This is also having wider trace. So this is how it should be. We should provide a wider trace so that inductance of this trace is less, which really fulfills the purpose of decoupling capacitor. What is the purpose of decoupling capacitor? Like it should, like there are three purpose. One is to have a buffer supply available for the device. Second is to reduce the um, um, noise which is captured in the line, right? And third is like sometimes these devices, ICs and some of the devices, they are kind of switching inside these ICs. We have transistors and other things. In intermittently, we need high current. If traces are long, they will have inductances, and we know if inductance is there, then we cannot suddenly change the current because that opposes the current change. So supply requirement sometimes is not fulfilled. So what happens if we place a capacitor very near to device? That sudden requirement or impulse supply requirement or requirement of current can be supplied by this capacitor without introducing any inductor or less inductor within the path. Okay. Another tip, magnetic field of any current carrying conductor can be confined within limit by providing a surrounding of ground plane. Mhm. Some of us might have heard many times like we usually provide a ground plane and all that. Yes. Why? Because this is a uh, Mini madam, can I request uh, someone like the noise continuously from there?
I will mute all the participants, sir. You're telling what is the problem?
Yeah, some noise I was hearing. Fine, madam. Thank you.
Okay.
Thank So we were talking about the magnetic field of any current carrying conductor can be confined within limit by providing a surrounding of ground. So if this conductor is alone, it has no other plane around it, you will find this produce some magnetic field and it will not have any receiver. Kind of, uh, yeah, okay. I think it's better now. Okay. Um, so if we provide a plane near the conductor, then all these magnetic field will be confined. So it will not go anywhere else to disturb any other trace or any other current. It will be suppressed here itself. Okay, so switching loop, all those traces can have its own returning path like a plane. There may be a ground shield around the control and sensing traces. So if they are really becoming very problematic, we can provide a shielding around that. Additional shielding. This is just a copper track at one side and copper plane at other side. The example of PCB. The top layer is having a trace, bottom layer is having a complete plane. So such planes are provided. Positive and negative traces of wires of a common signal. This is important. Common signal should run together and possibly parallel to each other. This is also like we heard about differential pair and all that while designing PCB. So this is like positive signal, which is same signal is going through one part, one line, and coming from another side. Every signal has should have a closed loop. It has one positive terminal, positive trace, and then it comes back through the negative. Common signal, the positive and negative wire of this common signal uh, should be run together and try like they should be possibly parallel to each other. So this is the effect like you can see here. all these magnetic field, they will not go out to disturb anything else. They will be confined within them. But sometimes people get confused with this thing that intersection of two control or two sensing paths should be avoided. This is two different, these are the two lines carrying different signal. Then they should not be parallel, they should not be close to each other. Even if there is a situation when we need to cross them, then they should be crossed like this. So better they should be perpendicular to each other. When this signal is coming here, this is here, we want to cross them. So crossing point should be something like this. You can make a perpendicular connection to each other wherever, whatever, how much ever possible. Should not be like this, like it is coming and we are crossing the signal like this. No, this should be avoided. This is a way like perpendicular to each other. We can provide such connections. Twisting of the positive and negative conductors carrying the same signal cancels line inductance. Like you must have seen such type of twisting. So if two wires are carrying same signal, then they will cancel each other's inductance because they both of them are having current in opposite direction, right? Same amount of current, same amount of magnetic field produced by them, but in opposite direction. So they cancel each other. And external earth shielding can be provided to loose and hanging wires and heatsink. These are additional, like if nothing is working, then we can provide shielding. Traces length should be wider than the minimum required for a particular value of current. Wider traces does not only for less resistive current path, but also reduces the inductance of the path. Be conscious while layout design, placement and routing of each and every component or trace. Uh, each and every component trace make difference. So while designing a PCB, whenever we pick up one component and we are about to place it, we need to think all other surrounding component, whether this is the correct position to keep it or we should place it somewhere else. Similarly, while routing, we should always route a wire while keeping all other surrounding wires in mind. Is this okay? No, nothing else is going to be disturbed by this. Then we can, like, we need to be very conscious while layout design. It takes sometimes months to design a PCB.